Good evening, all the members present today for this talk. It is ongoing series of talks at the platform of NASNI, National Astronomy Network of IAPT. Today we have with us Dr. Arvind Kulkarni. I welcome him on behalf of NASNI, Dr. P.K. Aluwalia sir, Dr. Madam Deka, and all other members present here. I welcome all of you. With us, Dr. Mangesh Suthar, founder of Brahman Darshan at Mumbai, and he has a huge, long experience of professional experience and involvement. Suthar is the founder of Brahman Darshan at Mumbai and has a long experience, over 2 decades of professional experience and deep involvement in the astronomy outreach through Brahman Darshan. Without further ado, I request Dr. Mangesh Suthar to kindly introduce our esteemed guest speaker of today's session and invite him for this talk.
He born in 1948 in Ranbanu in Agri district, north of Karnataka. His earlier education itself is a remarkable diverse. Almost like 1954 to 67, he studied in different schools in Karnataka, Maharashtra, Madhya Pradesh, and Mumbai. During his formative years of his education, he studied different languages, right from Kannada, Marathi. Also, since age 9th standard, he attended technical schools where, along with his regular curriculum, he was able to study basic engineering and gained valuable practical experience, thus earlier involving about multilingual education for his wide range of academic and professional journey. Dr. Kulkarni pursued his higher education in Mumbai. From Mumbai University, he completed BSc in Honors in Physics in 1969, followed by MSc in Nuclear and Experimental Physics in 1971, both from University of Mumbai. Later on, he moved to specialized field of astronomy and astrophysics and earned his PhD in astronomy and astrophysics from Anna University, Hyderabad in 1971. Recognizing the importance of effective teaching methodologies, Dr. Kulkarni continued to enrich his educational qualifications even after establishing himself as a scientific and educator. In 1992, he completed postgraduate diploma in higher education from Indira Gandhi National Open University, that is IGNOU. The most significant phase of his research came between 1974 to 78. Those 4 years actually were the very astronomical years for him, I would say. He actually spent almost 280 nights observing and studying a stellar system with 48-inch telescope, which was then the largest telescope available. Thus, extensive observational work demands scientific discipline, patience, accuracy, and deep commitment to understand the universe. This was really a significant phase in his career. His research continued, include 18 papers in observational astrophysics published in reputed national and international peer-reviewed journals. His work represents valuable contribution to the study of stars and stellar systems and reflects his strong foundation in observation. Dr. Kulkarni also had made outstanding contribution to public astronomy as well as science communication through his leadership of major planetary in India. From 1988 to 86, he was served as the director of Sardar Patel Planetarium in Vadodara, Gujarat. During his tenure, he developed 25 plus programs on astronomy and space science for students and general public. Thereafter, in 1986 to 1990, he served as the founding director of PM Birla Planetarium in Jaipur, Rajasthan, where he played a very central role in establishing the new planetarium and created 5 original programs for it. His contribution to the formal physics education has been extensive from 1990 to 19, where he taught undergraduate physics in 3 different colleges in Bangalore, serving both as the faculty as well as head of department of physics. Again, in 1992 to till 2008, he was associated with several undergraduate college as a visiting professor of astrophysics. From 1998 to 2014, Dr. Kulkarni taught physics and mathematics at IIT Delhi coaching centers in Bangalore. He also has long engagement with different students at educational level, has given him deep understanding of how the scientific concepts can be presented effectively to the diverse learners. Dr. Kulkarni has also maintained a long and active association with a lot of leading scientific and professional organizations. He has been a life member of Astronomical Society of India since 1975, completing almost 5 decades of association with the organization. He has been life member for Indian Association of Physics Teachers since 1986, representing 4 decades of sustainable environment involvement in physics education. In addition, he was also associated with Indian Physics Association for about 10 years and was founding member of Karnataka Physics Society. The remarkable aspect of Dr. Kulkarni's personality is that his intellectual curiosity has never remained confined to a single field. He has been always actively interested in history of science, technology, knowledge of systems, global affairs, development, equity, academic and cultural exchange. He strongly believes that education and cultural interaction can promote mutual understanding about people and nature. He is proficient in reading, writing, and speaking multiple languages like Kannada, Hindi, Marathi, Gujarati, and English. His multilingual ability has enabled him to be a communicator of scientific knowledge to a wide and diverse. Even today, Dr. Kulkarni, at such a profound age, he continues to explore and immerse areas of science and education. His current interests include introduction to quantum mechanics at a school level, promoting responsible use of artificial intelligence tools in learning and education, arranging orientation systems for schools and colleges. He has already conducted quantum mechanics sessions in several schools. He described himself as a learning devil, science and STEM community, and an emulator of artificial intelligence, quantum science, neuro-related knowledge across fields. So today we are very fortunate to have him with us to speak on a very highly significant and fascinating topic in NASNI's 39th talk, the James Webb Space Telescope, the first 4 years of James Webb Space Telescope. We'll understand how it has impacted our understanding of the world. As we understand that James Webb Space Telescope has completed 4 years, it is basically humanity's detective in observation astrophysics. Sentinel working for us, designed to send precious data of universe located more than million miles away on the outer side of the Earth, Sun and Earth line. This engineering marvel is working for last 4 years since 2022. Beaming humongous data for a wide variety of objects spanning our universe and is expected to continue beaming the large amount of petabytes of data for almost next 20 plus years. So this basically insight is emerging every single day of observation, and it will require at least 2 more slides to summarize and present details. This attempt only touches on the broad summary of the most important findings. So with that, I would like to welcome Dr. Arvind Kulkarni, and would like all of us to take the privilege of listening to his knowledge and insight. Over to you. Welcome, Dr. Arvind Kulkarni.
Yeah. Now, thank you very much for a very generous introduction, Dr. Mangesh Sutar from Mumbai. I'm very happy about the whole introduction you gave. Now, whether I deserve that much, I don't know, but then that is how it works. Now, the first thing I would like to thank Hemant Kumar for inviting me on this platform. Now, we will now the first thing. Then I would like to thank Dr. Ahurwalia and Lekhaji Purpare for this program. I'd like to say that what we are talking about regarding this, James Webb Telescope. The James Webb Telescope, Space Telescope's contribution reminded me of two important events in the history of science. I am going back to the history of science when physics, chemistry, biology, etc. were not very different, they were just the same. The first such event is 1774, almost 250 years ago, when we had Robert Hooke inventing the microscope. So when the microscope got invented by Robert Hooke and he starts seeing the cells of the onion and cells of the smaller scale, there was a huge revolution in science, especially in biological sciences. It went on to other areas like physics and chemistry later, and in the study of crystallography and all that. But that was the first similar punch. The second similar punch came around 1910 when Professor Cayal, C-A-Y-L, Cayal from Spain, he was basically a painter or a, a graphic artist. He made the sketches of the brain cells. The brain cell sketching happened in 1910, and in 1913 he got Nobel Prize for that in the area of physiology. Now, at the Robert Hooke's time, of course, the Nobel Prize didn't exist, but at least in the time of Professor Cayal from Spain, we did have this, and that is the second important breakup into neuroscience. So the people in general and everyone started understanding the brain in terms of the nerve cells and the connections. That was the second major change. I feel that this particular one, that is the data being rained, literally rained by, James Webb Telescope onto us from the rest of the world, is third such in that thing. So huge amount of data is going to come now. It has already started coming for the last 4 years, and we will have a lot many coming in another 7, 8 years for sure. And this is going to be a major change as far as the science is concerned. Now I will go to my slides and we will start the work on that. The major discoveries from James JWST are basically these, because most of the people who are joined would like to know what is in the pudding. I mean, they would like to eat first and then discuss the other formalities. First thing is what I call the impossible galaxies. I will explain all these 8 slides separately. Then second thing is too big and too fast. That is, we saw galaxies, the type of which we never imagined. The early galaxies. When we extrapolate from Hubble's law, we never expected that the galaxies so early will be so evolved. That. Second thing is too big and too fast black holes. We did not have black holes to be formed so early and so that big also. We thought that if we are looking at the earlier part of the universe, the black hole should be small, but that was not true. So these are the major two things. Third thing is sniffing the air of alien worlds. That is different planets. Now these are planets from other parts of the universe, not our own solar system or even our Milky Way necessarily. They can be from other things also. So these are the sniffing the air from alien worlds, that is basically planets, what I call as the extraterrestrial planets. Then come the piercing the dust of stars, star nurseries. Now the main contribution of James W is basically the infrared observation. And infrared observation allows us to pierce through the dust, and dust is no more a wall. So that is what has happened. So that is being shown in slide number 4. I'll be explaining each of these slides separately. Then the rogue free floating the Jupiter kind of pairs. So there are pairs of planets which are floating freely without having any attachment to their corresponding stars, like the planets attached to the sun. Then come the liquid water and comets. So close home from, notice that we are coming from impossible, we are slowly coming closer and closer. Now the liquid water and comets. So there is so much of liquid water available in comets here, like in the asteroid belt. Then come to the giant planets like Jupiter, Saturn, Uranus, and Neptune. So almost all of these planets have their own rings, and that is being seen more clearly here. And finally, the absolute dark hydrogen fog. We are not able to we didn't expect this absolute dark hydrogen fog, and we need to drive through this and figure out. Now I will try to basically how the universe switched on its light so early on is being the issue. Now, the first thing is the impossible early galaxies. The James W looked back to the beginning of the time and found bright, mature galaxies existing just a few 100 million years after the Big Bang. Scientists expected to find only small, messy clouds of stars, so These massive early galaxies mean that we have to rewrite our theories of cosmic history. This is a very, very important, challenging point. The next thing is too big and too fast black holes. We didn't expect black holes to form so soon. So James W. Supermassive black holes in the early universe we never expected. We knew about quasars, but the nature of quasars were not completely known. Astronomers previously thought the supermassive black holes took billions of years to grow, but James Webb tells us he discovered enormous active black holes in the infant universe, showing that black holes grew much more faster and earlier than anyone thought possible. I hope you recollect Dr. Sriram's lecture about a month ago when he spoke on active galaxies. So similar to that. Then analyzing alien atmospheres, general exoplanet. This is exoplanet. That is a planet doesn't exist in the solar system. It exists elsewhere. K218b atmospheric illustration. By measuring light passing through the atmosphere of distant planets, James W can sniff their air. If detected, it detected water vapor, carbon dioxide, methane, and carbon molecules on distant exoplanets like K1218b, helping us search for potentially habitable worlds. So the life we define is what is needed here: water vapor, carbon dioxide. Now, if there is life, other combination of planets of compound we do not know. Then piercing dust in star nurseries. This is a very important contribution from James W because it is basically a near infrared and infrared telescope. Stars are born inside thick clouds of dust called nebulae. Using infrared light, James Webb can see right through the dust of iconic regions like the pillars of creation as you see here, and uncovering thousands of newly forming baby stars that were completely invisible to older telescopes. Older telescopes do not see them because they were only in optical area, but this one is not in optical, but it is in near infrared and infrared region, and that is the reason. I would like you to note that the colors that you see may not be as realistic as they are in the sense that the colors are subsequently given to that. Basically, we have the information. So to make the picture more visible, the colors are provided. Then comes the rogue free floating Jupiter belt. This is very, very interesting. We thought that every planet has to be associated with some star, but that is not necessarily true. While studying the Orion Nebula, James W. spotted dozens of Jupiter-sized gas planets, as you see them, two of them here, drifting freely through space without orbiting any star. Even stranger is that many of these worlds float together in pairs, baffling scientists who are trying to explain how they got there. We are still not sure how. Now, while studying the Orion Nebula, James W spotted dozens of Jupiter-sized objects drifting nearly through space without orbiting any star. Even stranger, many of these worlds float together in pairs, baffling scientists who are trying to explain how they got there. What I'm trying to say is that I'm bringing in the issues that are not known. Now, liquid water vapor on main belt comets. This James Webb examined Comet Reed. Comet Reed is the name of the comet inside our solar system's main asteroid belt and detected water vapor around it. This proved that icy water can survive in warmer regions close to the sun, supporting the idea that ancient comets brought oceans to the earth. So notice that because of water we exist. So this is a very important thing for us. The next thing is the rings and storms of our gas giant. This is very interesting. James W. captured high definition infrared images of Neptune, Jupiter, Saturn, and Uranus. It revealed Neptune's extremely faint dust rings, Jupiter's bright auroras and turbulent storms, and the complex atmospheric layers of Uranus like never before. So, the study of planets within our solar system, but that are big in size. That is the way. The last one here is how the universe switched its lights on. In the early days, the universe was filled with a dense, dark hydrogen fog. James Webb showed how the light from very first stars and galaxies gradually burned through this flaw, clearing transparent bubbles of space and letting light travel freely across the dark, across the entire darkness. Then we go to the mapping of the invisible scaffolding of dark matter. Now, this dark matter is something very, very interesting, which was not talked about 30 years ago. Dark matter is invisible, but its strong gravity bends light passing nearby. By measuring how light from deep space is distorted, James Webb Telescope created high-definition maps of these cosmic webs, as you can see in the picture here, showing how dark matter acts as invisible framework holding galaxies together. What the dark matter does is it does not show itself, but it definitely behaves in bending the light coming from behind, and that is why these map-like things you are able to see. Then the puzzles of the little red dot. This is exactly what we have not understood. James Webb discovered hundreds of tiny, bright red objects in the ancient universe. Why they are red is it is being redshifted, they are running away. Scientists are still debating what they are, either extremely dense galaxy cores jammed with millions of stars or maybe supermassive black holes trapped inside surprisingly compact spaces. So you can see the picture of three of them in detail, and otherwise so many these red little dots are there. There is no clarity on this so far. Then come early galaxy collisions. Scientists used to think that early galaxies evolved in isolation, but James Webb captured live, tightly packed galaxies. This is some kind of five galaxies together, crashing together less than a billion years after the Big Bang. The collision spread vital heavy elements like oxygen and carbon into deep space, and we really do not know how these five galaxies together ever existed. Just see that we are not able to extrapolate what we did. For example, if we, by extrapolation, I mean like this, if a 10-year-old child has a certain size, 3-year-old should have probably smaller size. This is okay as far as the human babies are concerned. But that kind of a thinking, linear thinking, is not true here, and that is what the early galaxy collisions are telling us. So the galaxy killing wind, this is a very important thing. James Webb captured powerful galactic gas blasts, as you can see in the picture here, pushed out by feeding black holes and massive star clusters. These superfast winds blow away all the surrounding gas, starving the galaxy and stopping it from forming the new stars. Dr. Sriram spoke about 1 month ago regarding his active galactic nuclei, and he talked about the light going at the matter going at almost zero point 0.7 to zero point 0.8 times the speed of light, and we do not understand what is happening. This is a very important slide here. Then come feeding the hidden planets in dust disks. Young stars are surrounded by thick, blinding disks of dust where new worlds are born. James Webb can detect unique light signatures of chemical gases because of what we call as the spectrophotometry, such as methane and carbon dioxide, the signature of which we know thoroughly, allowing scientists to locate hidden planets tucked away inside these dusty clouds. This is another contribution of atmospheric composition, finding hidden planets in dust disks. Okay, these are the major things that we spoke about 13 of them. There are a few more, but I have identified only 13 major ones, and maybe in another discussion we can take the minor ones later. But let us sync with what we have. Now, coming to the James Webb Telescope, a brief history may be in order. A brief history, you can see the James Webb Telescope here. As you know, the idea of James Webb started long ago. First seeds of Space Telescope Science Institute in 1989. So we are basically talking about 40-year old story. So 40 years ago, the astronomers convened at the Space Telescope Science Institute to brainstorm a successor to the Hubble Space Telescope even before Hubble was launched in 1990. The core realization was that expanding universe cosmology redshifted light from early galaxies to infrared, requiring an infrared optimized space telescope, and that was the rationale for it. So we are starting almost 1989, that is 26 plus 11, about 37 years ago. Then HST and beyond 96. This is the new generation space telescope. The Dressler Committee formally recommended building a next generation space telescope. The report called for a passively cooled infrared sensitive observatory with a primary mirror greater than 4 meters in diameter placed at the Earth Sun Lagrange point 2. I will come to that just now in a while. Next is uh, renaming the renaming the major contract and award. This may not be very interesting for you, but I would like you to know that science, enterprises anywhere have their own human elements. So NASA officially renamed NGST to James Webb Space Telescope after NASA's second administrator. I would like you to note that James Webb was neither an astronomer not an engineer, not a technocrat, but he was an administrator. And it should tell us that administrators have their own value in running huge science, enterprises like this. Who led the Apollo program? He did it from 1961 to 69 when President Kennedy was there. So this TRW, later acquired by Northrop Grumman, was selected as a prime contractor to develop the folding of 18 beryllium segment primary mirrors and deployable tennis court size sun shields. Rebaselining and engineering overall. Then it took some time, facing significant budget overruns. So when this budget overrun happens, don't worry about it. In our own backyard, the Calcutta metro started. You know that Calcutta metro was the first one in the West country. The earliest Calcutta metro the estimation was 80 crore, but by the time it got completed, it went to not up to almost to from 80 crore to about 2000 crore. So if it can happen in our own backyard, it can happen anywhere. So the significant budget overruns were there, design complexity and political scrutiny. The project was restructured. NASA instituted a rigorous testing and rebaseline plan, acknowledging that a telescope operating at 1.5 million kilometers from Earth had to work perfectly on its first try, as servicing was impossible. So there is no question of servicing as in the case of Hubble and other telescopes, but in this case it is required. Integration and launch happened in 2021. After decades of engineering breakthroughs on cryogenics, segmented optics, and deployment mechanisms, James Webb launched on Ariane 5 rocket from French Guiana on December 25, 2021, successfully deploying its mirror and sun shield en route to Lagrangian point 2. Notice that from December 25, it took 6 months for the whole thing to reach there and get adjusted. These are the Lagrangian point, nature's 5 equilibrium points. You can see sun on the left side and the point on L2 is what we are talking about. L1, L2, L3, L4, moon and L5. Then these are the Lagrangian concept. Then comes Y. L1 is clear. Notice that the combined pull is 0 here. But in L2, it is combined gravity. So there is a pull from 4 as well as this. The stabilities of L4 and L5 are discussed at L4 and L5. Just a little change in the stability smooth to the gravitational potential is such. All 5 holes are discussed in the last one. So this is a general. Now, if you want to understand entirely the Lagrangian bond, we will need another class for that, for which we will see later. Now, location directly between two bodies, between Sun and the Earth. Why it works that if you put a small satellite at L1, I'll go back to L1, the intense gravity from the sun pulls it towards the sun at the exact same point. Earth's gravity pulls it backward, and the outward centrifugal force also pulls it back. L1 is a perfectly balanced spot where the pull of the sun is exactly equal to the pull back towards Earth. It's a great place to put sun observing satellites. But we are not observing the sun. Therefore, L1 is not suitable. We go to L2. Behind this behind the small on the opposite side. 1 minute. Aside from the larger body, behind the smaller body on the opposite side from the larger body, Earth between L2 and the Sun. Uh, you see that why it works that at L2 the combined gravity of the Sun and the Earth are both pulling the satellite inward towards the left. Towards the left, I mean this L2. L2 I'm saying. Both are pulling. Look at picture number 3 on the right hand top, and you see that at L2, the combined gravity of the Sun and the Earth are both pulling the satellite inwards. This combined force is extremely strong. However, at L2, the object is further out, so the outward centrifugal force is also much stronger. L2 is where this massive outward push is perfectly equal to the powerful inward pull. Therefore, L2 is famous because the Earth blocks most of the sunlight. That is what we need, keeping telescopes extremely cold, essential for seeing faint distant galaxies. Why it should be cold is that we need temperatures which are extremely small. I'll come to that in a while. Location now, behind the large body on the opposite side of the central thing, Sun is between L3 and Earth, as you see here. Sun is between L3 and Earth. L3 is difficult to observe because the Sun is in the way, but its existence follows the same rule. At L3, the gravity from the Earth is minimal because it's so far away. But the gravity of the massive Sun is powerful. The outward centrifugal force at that distant point is just enough to counteract the Sun's pull, creating a balance. Then comes the next one, namely L2 and L4 are special. L1, L2 are unstable equilibrium. They're like balancing a ball on the top of your nose. So nudge slightly and it will fall off. It will accelerate. L4 and L5 are inherently stable. They're like balancing a ball in the bottom of a smooth bowl. If you nudge it, it will settle back down. Location L4 is 60 degrees ahead of the smaller body of the orbit. L5 is 60 degrees behind. For the Sun-Earth system, they form two equilateral triangles with the Sun and Earth as the vertices, as the picture is seen here. Why they work is the combined gravity of both large masses pulls directly toward the center of the orbit, which creates a stable gravitational well. From small bodies and dust can get trapped here naturally. We actually see groups of asteroids called Trojan asteroids orbiting at L4 and L5 points of other planets like Jupiter. The Lagrangian points are unique astronomical landmarks. They are not physical objects but areas of gravitational equilibrium. Understanding them is vital for exploring our solar system because they allow us to position observatories with minimal fuel, creating permanent outposts to watch the Sun, then peek deep into the cosmos, L2, to study natural asteroid clusters, etc. As you remember, we have L1, our own Indian, ISRO's AstroSat is at L1 there, which is observing the Sun. Okay, then who is this James Webb? As I discussed, James Edwin Webb was an American public servant and NASA administrator, best known for leading NASA during Apollo era from 61 to 68 when President Kennedy was there. You know that Kennedy gave, in 1961, Kennedy gave the political statement that we should have an American in 1969. And of course, he didn't remain alive till that time. He went 20th July 1969. And this man was responsible for that, technically. NASA named the James Webb Telescope after him because his major role in shaping the US space program. This is just a telescope. I'm just saying that the big telescope we are talking are very similar to this, just to get in all the people thinking that this is what we are doing is basically a telescope like this, but its size and location and these things are more. A telescope for astronomy is an instrument that no, I don't need to tell the people who are experts here, but those who are not expert and are new to astronomy, they may need this simple information. That is why this slide finds place here. Now, we talk about some take-home points. If you have any questions, please write it in the chat box. I'll be answering. Some take-home points are cosmic assembly, small, chaotic, and brightened. Now, what was expected and what was observed? What was expected was prior to launch, cosmological models predicted that early galaxies forming 300 to 400 million years after the Big Bang would be small, dim, and primitive protogalaxies. This is our thinking that if my 10-year-old child is this big, then for 6 years, 7 years, their size keeps increasing. That is a linear thinking, but the world does not go that way. Our thinking is linear, but the world doesn't seem to exist in a linear way. James James Webb. Now, what was observed was it has uncovered bright, surprisingly massive, and highly structured early galaxies, along with mysterious little red dots. This proved that galaxy formation occurred far faster and more efficiently in the in the infant universe that standard models had allowed. Okay, so the standard models need to be substantially changed now. Black hole growth, slow accretion, and precocious giants. What was expected as astronomers anticipate that supermassive black holes hold billions of stars of gradual gas consumption to reach millions and billions of solar masses. But what was observed was totally different. James Webb fully found supermassive black holes actively feeding in the universe's first few 100 million years. This forced astrophysicists to reconsider whether black holes grew via rapid, heavy seeds or direct gravitational collapse early on. So you see the amount of change in direction we need to address. Then the next thing is exoplanet science, basic detection versus precision astrochemistry. What was expected was James Webb was expected to confirm the presence of atmosphere around major exoplanets and detect simple signatures like water vapor. But what was observed was something like this. Beyond mapping atmosphere profiles, detecting carbon dioxide, methane, and water worlds like on planet K218b, James Webb opened entirely unexpected doors, such as discovering untethered rogue jumbos. Jumbos mean Jupiter-Mars binary pairs, drifting without host stars, challenging planetary formation dynamics. So almost every branch of, of astronomy and astrophysics has a challenge now to meet the observations of James Webb Telescope. Then the cosmic reionization, this is a very important thing, cosmic reionization, sudden flash versus gradual bubbles. What was expected was scientists sought to pin down the exact epoch when the universe's neutral hydrogen fog cleared by the first starlight, which we call as the era of reionization. What was observed was this. James Webb revealed that ionization was not a sudden uniform event driven solely by the rare megastars. Instead, it was a patchy, localized process where early dwarf galaxies gradually carved out expanding, transparent bubbles of clear space across the cosmic fog. All these things you have seen in the slide, I will show them at here. Lastly, the paradigm shift from confirming models to rewriting textbooks. This is very important. It's very, very important, especially most of the people being teachers here. You have to, if you are thinking of writing textbooks, they will have to be according to what James Webb has told us. What was expected is that JSW was primarily designed as an engineering masterpiece, meant to extend Hubble's observations deeper into the infrared spectrum and fill the known gaps in our timeline. But what was observed was rather than merely confirming existing physics, James Webb actively broke key predictions across cosmology, stellar evolution, and planetary science, demonstrating that the early universe was far more active, interconnected, and complex than previously imagined. I'm sure most of you know that people like Reed, etc., they are doubting this 13.8 billion story also. So with this, I have finished this slide. Now, with this, I stop my presentation. I am the screen.
Thank you, Arvind sir. It was really a great session about beginning about the James Webb Space Telescope. And as it has almost spent 4 years and huge amount of or humongous amount of data is being from the telescope and available for further research. The session is open for everyone to have their question. Either they can raise their hand and there is a question.
Yeah, is the James Webb Telescope fixed at a single point in space, or does it orbit around the sun point? If it orbits, what is the approximate radius of the size? Okay, James Webb Telescope is apparently not fixed. As far as the Earth is concerned, it is fixed, but it is in the sun-Earth line on the other side of the earth, because so that it will never face the sun. On the other hand, the solar panels will, now the temperature at which it operates goes from minus 269 Kelvin to about 360 degrees. For that we use a material called kapton. I will describe later. The answer to the question is it does orbit around the sun, but without hurting us, because it is not fixed in space. The approximate radius of the size of orbit is around 1.5 million kilometers. 1.5 million kilometers.
Dr. Kulkarni sir, these rogue planets you are referring to, so rogue planet without having any star or any other support. What is the mechanism of such objects floating in the space, Dr. Kulkarni sir?
Planets which are not attached to any of the suns. So first thing is that planets exist only attached to their suns is no more true, because there are so many free, planets moving around. And these are found in other galaxies, our own galaxy also, and other galaxies also. And this is possible because of the infrared observations. Mechanism floating, that they will be moving unattended, and if some other star or something is in between it, they will get attracted to that. They are rogue in a sense that they do not follow. They are not part of a particular family as such. In that sense we call it as rogue planets. They have left the family of the sun, and then they can go anywhere, wherever they go. If they happen to come across a star after a few 10 or 100 years, they will get attracted to that and get locked into that. Yeah.
For the presentation, it was very informative and encouraging.
Thank you.
So my question is the James Webb data publicly available, and is it clean, sir? Is it ready to use, or we have to do image processing and all that?
No. At this point in time, the data is not that publicly available. Some information they are releasing, because they want to, of course, since it's an American, European, Canadian project, they would like to make use of the data. The data is not publicly available. Some pictures definitely are available. Some pictures are available, and they guardedly release the data. Something is there. So the answer to your question is pretty much no. Very in a small quantity, yes.
All right. Thank you, sir. You're speaking to Simon from Uganda, and I have some other listeners from Uganda. They are viewing. Thank you for your presentation about James Webb Telescope. We have learned, and also we would love also to get in touch more in terms of these conversations more. I'm a space analyst, and we are going to celebrate World Space Week in Uganda. So we're going to nationalize it in Uganda around October 3rd to 4th. So would love to get in touch with the Indian Society. I'm speaking to right now about space, National Astronomy Network, and also we get in touch with people about mind, yeah, so that we get in touch. How best you can help us walk in this journey, support us. Yeah, that's it.
Thank you very much, sir. Thank you, Kulkarni sir. It was really enlightening and a very informative talk, James Webb Space Telescope. I will also request Dr. P.K. Ahluwalia sir for his comments on this talk.
So a very good evening to everyone. And I think today was a very special lecture for us. For the audience who may be new here, I would like to say that Professor Kulkarni has been the initiator of this whole program called NASNI, National Astronomy Network. And he is what we call as a Sutradhar for that. And he gave us a wonderful lecture, a very good exposure to this very interesting project of putting a telescope into the deeper parts of our solar system and to see beyond that. It was really very enlightening, encouraging, and we are now in the 40th uh, you know uh, talk, which is going to be the next talk. That means for so many weeks we have been really listening to these talks, and I must thank Professor Kulkarni for keeping us on our toes in making us reach out to the experts and talk to us. So, Professor Kulkarni, thank you very much for all the effort which you had made. The slides were beautiful and they were self-explanatory. I think that shows what a wonderful science communicator you are. And I think we have some lessons to take from you. I hope you will not now leave here, but will come out with your second and third version and extension of this set of lectures which you have initiated. And you will not keep us waiting for that also. So once again, on behalf of IAPT and on my personal behalf, I thank you for all the encouragement and for today's wonderful lecture. Thank you very much.
I want to express my thoughts at the end, saying that the slides, of course, were selected, but the arrangement was made by my son, and another set of slides I have, which my grandson made in US. I would like to show that, but that we will see for some other time. They're also equally nice. But it is nice of you to have invited me and give me an opportunity to, discuss. Thank you very much. Namaskar.
I would like to invite Madam Ranjita Deka for a formal vote of thanks.
Okay.
Respected Professor P.K. Ahluwalia, sir, President IAPT, respected Dr. Arvind Kulkarni, sir.
Thank you.
Dear participants, a very warm thank you to Dr. Arvind Kulkarni, sir, for his enlightening talk on the James Webb Space Telescope and how it has transformed our view of the universe. Your passion for science communication is truly inspiring. Thank you to Professor Ahluwalia, sir, for his leadership and continued support to IAPT and NASNI. My thanks also goes to Professor Hemant Kumar, sir, for organizing this wonderful lecture, and to all of you who joined us this evening. We look forward to seeing you at the next NASNI talk. Thank you once again.